Assalamualaikum and hi everyone, we are from group 3 and today we are going to present experiment 7, which is estimation of heat capacity and entropy generation. Introduction. Heat capacity tells us how much heat a material can absorb before its temperature change. By measuring the temperature change of the metal and the vinegar and using the known heat capacity of vinegar, we can calculate the heat capacity of each metal. When a hot metal is dropped into vinegar, heat flows from the metal to the vinegar until they reach the same temperature. This process is not 100% efficient and results in entropy generation, which reflects the amount of energy that becomes unavailable for work due to irreversibility in the heat exchange. Estimating this entropy helps us understand the second law of thermodynamics in practical situations. The objective of the experiment is to estimate the heat capacity of different metals provided and to estimate the entropy generated when these metals are dropped in a container containing vinegar. The scope for the experiment is first, the metal blocks used in this experiment are copper, aluminium and iron. Second, the mass of vinegar used is 87.7 gram. And then we record the temperature of the vinegar in the second beaker every 20 seconds until 3 constant values are observed. And then the room temperature is 28 Celsius and initial temperature of vinegar is 90 Celsius. And lastly, the media used is limited to vinegar.
So for Turing and working principle, the first one is the heat capacity. So the core goal is to determine the specific heat capacity (Cp) of the metal sample. So in this experiment, we use the metals such as the aluminium, iron, and copper. So when a hot metal is dropped into a cooler vinegar, it will lose the heat, which is gained by the vinegars. And by measuring the initial and final temperature of both the metals and the vinegars, and knowing that the vinegar's heat capacities and the metal heat capacity can be estimated by using the formula. So the formula is shown on the right hand side. The Q loss metal is equal to Q gain vinegars. This formula also can is equal to MC delta T. So M is the mass, C is the so for the left hand side, the M is the metal mass of the metal, C is the specific heat capacity of the metals, and the delta T is the change in temperature of the metals. And for the right hand side is equal to the M vinegar, which is the mass of the vinegars, and Cp of the vinegars, and delta T of the which is change temperature of the vinegars. After that, we can see the above one got the theoretical Cp for aluminium metal, which is 0.887 kilojoule per kilogram Celsius, and Cp for the copper metal is the 0.385 kilojoule per kilogram Celsius, and Cp for the iron metal is the 0.462 kilojoule per kilogram Celsius. So considering the typical acid concentration in the vinegars, the specific heat capacity of the vinegar is estimated at 2.05 kilojoule per kilogram Celsius. So the second theory is the first law of thermodynamics. So this law, also known as the energy conservation, that underpins the entire matter, which is the delta U is equal to Q minus W. So the delta U is the change in internal energies, and Q is the heat, and W is the work. So we can see from the right of the table, when the delta U is bigger than zero, the system gain energy. When less than zero, so the system will loses the energies. So the Q, which is the heat, when equal to when bigger than zero, so the heat is absorbed, and less than zero, the heat is released, which is exothermic. And the work done by the system, bigger than zero, the system does the work on the surrounding. When less than zero, the work is done on the system. So in this case, there is no work done. So delta U, which is internal energy, is equal to the heat. So the heat lost by the hot metal is equal to the heat gain by the vinegars. So we can use this formula. The heat metal is equal to negative heat vinegar. So the heat metal is the heat loss, and the heat vinegar is the heat gain. So the negative sign indicate that the heat flows out of the metals and into the vinegar. So the third one is the second law of thermodynamics. So it said that the heat naturally flow from the hotter metals to the vinegars. So this law explains why energy transfer is one way without the external force, and also justify why it cannot perfectly recover all the heat energy, because some of the energy will become unavailable for useful work due to the entropy generation. So we can see from the diagram here, and the heat will flow from the hot to the cold. So the hot metal to the cold vinegar. And the last one is, which is the entropy. So it's that as the heat is transferred from the hot metal, which is high temperature, to the vinegar, which is lower temperature, the entropy will increases. So the entropy change can be estimated by using the following formula. The first one is the entropy change for the metal is equal to MC ln T. So the M is the mass, and the C is the heat capacity, and the ln T is the temperature. T2 is the final temperature, and T1 is the initial temperatures. So for the entropy change for vinegar also same as the entropy change of the metal, also by using the epsilon T, and the total of the entropy change is equal to the entropy change of metal plus the entropy change of the vinegar. So for the metal, the entropy will decreases as it lost the heat. For the vinegars, the entropy will increases as it gains the heat. So the net entropy change, which is the delta S total, will be positive due to irreversible missing and temperature difference. So which reflect the real world inefficiency.
Okay, then this is our experimental setup. We got a electronic balance, thermometer holder, thermometer, digital thermometer, and also rubber glove. And we got three metal blocks, which is aluminium, iron, and copper. And we got hot heater, which is the hot plate, and vinegar as our substance. And we got bigger aluminium foil and metal hook. After that is the methodology part. First step is to weigh the copper metal block using electronic balance. Then weigh the mass of empty 100 ml beaker at first using electronic balance. The third step is to pour the vinegar into beaker A until it reaches 90 ml. Then the filled beaker was measured again and the mass of vinegar was calculated using the equation mass of vinegar equals to total mass of beaker A with filled vinegar minus the mass of empty beaker A. Then place the beaker A on a hot plate and begin heating. Submerge the copper block in the heated vinegar using a metal rod using with a hook, ensuring it is fully immersed. Then heat the vinegar until it reaches a temperature of 90 degrees Celsius. Measure the temperature of vinegar using a thermometer. Assume that the copper block has reached the same temperature as the vinegar. After that, as the first beaker is being heated, slowly pour vinegar into the second beaker. Continuously measure its total mass until it equals the total mass of the vinegar in beaker A. The beaker B is then covered with aluminum foil to minimize the heat loss to the surroundings, and simultaneously measure and record the initial temperature of vinegar using the digital thermometer. Then, when the vinegar in the beaker A reaches 90 degrees Celsius, use the metal rod with a hook to swiftly remove the copper block and promptly transfer it into beaker B containing the vinegar. Then cover the top part of beaker B with aluminum foil once more. We record the temperature of the vinegar in the beaker B every 20 seconds until two consecutive constant temperature values are observed. After the temperature recorded, proceed to get the value of specific heat capacity, which is Cp, for the copper block using this equation that is shown in the theory part. Then calculate and compare the experimental and theoretical specific heat capacities by applying the percentage error formula. Then present the result in a bar chart for clear visual comparison. After we get the heat capacity, we can calculate the total entropy change of the system using the formula shown at below. Then identify potential source of error, such as heat loss, slow metal transfer, and inaccurate temperature readings by minimize them using insulation, quicker handling, and precise instruments. And the last step is to repeat step 1 to step 14 using the iron block and aluminum block.
So this is the result. We have the table of mass, which is the empty beaker, filled beaker 90 ml, copper block in kg, aluminum block, and so iron block. These are the values that we have. And we also have the table 2, which is the data of vinegar temperature for each metals. And we recorded of each and every block every 20 seconds for the equilibrium temperature for each of temperature, and we calculate the equilibrium temperature. So we also have the table 3, which is the data of specific heat and entropy. Our vinegar heat capacity, it's the 2.05 in kilojoule per kilogram Kelvin. And we had for copper, aluminum, and iron. For specific heat capacity for copper is 0.34, 0.547, aluminum is 0.8, 0.9, iron is 0.412, and we have the entropy change as well. The entropy change of vinegar, the entropy change of metal, vinegar, and also the total entropy generated, where the total entropy generated is 0.00609 for copper, 0.00476 for aluminum, and also the iron 0.000649. Moving on with sample calculation, we had the sample calculation for the copper. We have their mass as it's 0.1215 kilogram, and we had the initial temperature, which is 363 0.15 Kelvin, and final temperature of which is the T2, which is 312.95 Kelvin. Same goes with others. They have different values, especially for vinegar, and also this is the example sample calculation for only copper, and we had the heat loss by copper equals to heat gain by the vinegar by using the formula of mass MC theta T equals to MC theta uh, T, which is the mass of copper multiplied by the heat capacity of copper, uh, then multiplied by the change of temperature of copper, T2 minus T1, and equals to the mass of vinegar multiplied by the heat capacity of vinegar, and also multiplied by the temperature change of temperature of vinegar. So with that, we're able to calculate the capacity of copper, heat capacity of copper. That's one of the example calculation, and we did also calculate the entropy of copper and vinegar to get the total entropy of these values, and the total entropy of the entropy of copper is MC ln T2 over T1, which is for copper side, and also vinegar side, same as well. Entropy of vinegar equals to mass of vinegar multiplied by the heat capacity of vinegar ln T2 over T1 of vinegar. So as we get the entropy of copper and vinegar, we will add up to get the total entropy, which is total entropy S equals to entropy of copper plus total entropy of vinegar, and we will get their total entropy value, which is 0.00609 as previous result table. This is for the copper and vinegar. And we continue with same as well for aluminum and also vinegar, the same method and approach, as we use the heat loss by the aluminum and heat gain by the vinegar, MC theta T equals MC theta T, and also the entropy as well. We will try to find the total entropy by adding the entropy of aluminum and also entropy of vinegar. So when we add up, we get the positive total entropy, which is 0.00476 kilojoule per Kelvin for the aluminum and vinegar. As for iron, same again. We will use the same approach by evaluating the mass, by finding the mass, the initial temperature T1, find temperature T2 of iron, and the for vinegar as well, the capacity, mass, and temperature 1 and temperature 2. Then we will use back the same thing, heat loss by iron and equals to the heat gain by the vinegar, MC theta T equals to MC theta T of iron and vinegar. Then we will find the entropy of iron using the MC gone T2 over T1 as for iron, and also same goes with entropy vinegar MC ln T2 over T1 vinegar, and we will try to find the total heat entropy equals to the total entropy of iron plus entropy of vinegar, and just add up, and we will get the total entropy of among iron with vinegar, which is 0.0000649 kilojoule per Kelvin. That's for the sample calculation. From the result, we can know that aluminum shows the highest CB heat capacity among the three metals in both experimental and theoretical values. In all case, the experimental heat capacity values are lower than the theoretical ones, and this difference is expected and commonly observed in laboratory conditions. As the discrepancy between the experimental and theoretical values can be attributed to several factors. The first one is heat loss to the environment during the transfer of metal into vinegar. And secondly, the incomplete thermal equilibrium between the metal and the vinegar. the inaccurate temperature readings due to the human error or parallax error, and the evaporation of splashing of vinegar, especially at high temperatures, and it might be also the delay in transferring the heated metals, causing it to lose heat to the surroundings. So for the discussion, the question is the identify the types of metal given and compare your estimate heat capacity with the literature of existing data. Plot a bar chart of CP, discuss about the total entropy generated during the above process, and discuss and others discussion. So for the first one, it's the calculation of error, where we want to know that errors existed among these three um, metal block, and we had the equation to calculate the errors, and the error is the percentage error equals to the uh, heat capacity experimental minus the heat capacity of theoretical value, uh, modulus over the heat capacity of experimental value multiplied by the 100%. So with that, we calculate for copper, aluminium, and iron. We get copper error for 11.55%, aluminum for the it's 8.74%. For iron, the percentage error it's 10.71%. So we also plot the bar chart of the specific heat capacity, the specific heat comparison between theoretical and experimental for different metals, which you can see from here. The copper block is the lowest among all, and the highest one is the aluminum. It goes with aluminum, iron, and copper. So yeah, it's the same as for the theoretical and experimental value. So we can see from the as presented from the result, the total entropy and also the percentage error, and also the theoretical and experimental specific heat capacity result. And from that result, we can discuss that the discussion of the on the total entropy generated during the process, where the total entropy of the system can only stay the same or increase during any physical process. It can never decrease. If there's no change in entropy, the process is reversible, and increase in entropy indicates that the process is reversible. In our case, the calculated entropy change was positive, which suggests that some experimental errors occur because there might be some errors because of theoretically there should be no change in entropy for reversible process. The process is ideally reversible because the thermal equilibrium is eventually reached between the vinegar and also the copper, iron, and aluminum block, allowing the blocks to be reheated and the process repeated. So, as discussion mentioned, the sources of error and ways to reduce time is to the parallax error can occur when misreading instruments like thermometers, uh, or inaccurate vinegar volume may result due to the absence of a measuring cylinder, which are not accurate in measuring the volume. Heat loss may happen as the beaker is not properly insulated, as like when we cover the beaker using aluminum foil. It's not properly insulated. For with that case, how to reduce this error, we always take readings at eye level 90 degree to avoid any parallax error. And we also should use measuring cylinder to accurately measure 90 ml of the vinegar before pouring it into the beaker. We just transfer it from the measuring cylinder. And also we should ensure the beaker is well insulated to prevent heat loss to the surrounding, like maybe cover it with aluminum foil tightly, or properly without any heat loss to the surrounding. As for the justification for stirring the vinegar in the container, when the metal blocks are placed in the vinegar, it is essential to stir the vinegar continuously to ensure that the heat from the metal blocks are evenly distributed. This helps in achieving uniform heat transfer throughout the vinegar, improving the efficiency of the process and reducing the possible errors. As for justification for quickly transferring the hot metal into the vinegar, the metal blocks, once removed from the heater, is much more hotter than the surrounding air and will start to lose heat to the air immediately. Since we want the heat to be transferred directly into the vinegar, it is important to move the metal block quickly, or by doing so reduces heat loss to surroundings and helps to obtain more accurate results by preserving the intended heat transfer.
Okay, next for the safety procedure. First, the personal protective equipment (PPE). We need to wear lab coat, safety goggles, and heat-resistant glove. The reason is to protect against burns from hot surface, accidental spill or reaction that may release heat. And secondly is use proper thermal insulation and handling tools. Use insulated tongs, clamps, or holder to handle heated component. The reason is to prevent direct contact with hot equipment that can cause serious burn. Okay, number three is check equipment for defects before use. Inspect electronic balance, heaters, and digital thermometer or malfunction. The reason is faulty equipment may lead to inaccurate measurement or hazardous electrical or thermal accidents. Number four is preventing spills and burn. Keep the experiment area clear of clutter to avoid accidental bumps or spill. Allow all heated material to cool before handling or disposals. Number five is to keep your eye level perpendicular to which is horizontal to the liquid column meniscus. This ensure can get an accurate temperature reading. Looking from above or below can cause parallax error, where the reading appears higher or lower than the actual value. And lastly is minimize heat loss to surrounding. Wrap the second beaker with aluminum foil to minimize heat loss to the surrounding.
So in conclusion, these experiments aim to determine the specific heat capacity of copper, aluminium, and iron by measuring their thermal interaction with vinegar. Additionally, it evaluated the total entropy generated during the process to assess the irreversibility of the heat exchange in accordance with the second law of thermodynamics. So below is the table that contains the experimental CP, theoretical CP, percentage error, and total entropy generated. So as we can see from the table, the percentage error is below 15. So this means that the experimental CP is quite close to the theoretical CP. The experimentally CP values were in the cross agreement with the theoretical CP values, demonstrating the effectiveness of the applied method. The entropy generated in each case were positive and minimal, indicating that although the system approached the equilibrium, the heat exchange was irreversible. So for the specific heat capacity, it mean that the specific capacity is the amount of the heat needed to raise the temperature of the 1 kg of the substance by 1 Kelvin. So the measured specific capacity are as follow. For the copper is the 0.3405, aluminium is the 0.8094, and the iron is 0.4125. So all the unit are in kilojoule per kilogram Kelvin. So the result follow the expected trend, which is aluminium is bigger than irons and bigger than copper. So the aluminium is the biggest. Aluminium needed more heat to increase in temperature as and the copper heated up the fastest. So the small percentage error, which range from the 8.74% to 11.55%, indicates that the result was fairly accurate. Okay, so for the entropy change, the entropy measure the disorder or energy spread in the system. So the metal lost the heat, so their entropy decrease, and the vinegar gains the heat, so its entropy will increases. So the total entropy change, which is the total entropy change of metal plus entropy change of the vinegars. So we can see here the for the copper is the positive 0.000609 kilojoule per Kelvin, and for aluminum is 0.000476 kilojoule per Kelvin, and iron is positive 0.00009 6 0.000649 kilojoule per Kelvin. So the positive total entropy means the process were irreversible as expected, and confirm that the second law of thermodynamics, which state that the total entropy in real process will increases. So the measured specific heat capacity follow the expected trends, which aluminum exhibited the highest heat capacity, followed by iron and copper show the lowest heat capacity. This trend align with the standard material properties and validates the approach taken. The minor discrepancies between the theoretical and experimental value likely stem from the experimental limitation rather than the procedure's error. So for the calculation of the entropy change for both the metals and the vinegar reveal that the negative entropy change is the metal, which is the heat loss, and the positive entropy change in the vinegar, which is the heat gains, and the net positive entropy generations that satisfying the second law of thermodynamics. So this confirmed that the energy was not perfectly conserved as a useful work, and some were dissipated, resulting in an irreversible process. So for the sources of error and limitation, several factors may be contributed to the derivation in the result. The first one is the heat loss to the environment due to the lack of insulation and non-uniform heat distribution within the metal block, and the imprecise temperature measurement at initial or equilibrium stages, and assumption of perfect thermal contact between the metals and the vinegars. So the recommendation for improvement is to enhance the accuracy and reliability of the future experiments. The following improvement are recommended. So the first one is use a well-insulated calorimeter to minimize the heat exchange with the surroundings, and apply the continuous steering to ensure the uniform temperature distributions. Utilize digital temperature sensor with higher precisions, and measure the exact mass of the vinegars instead of relying on the volume approximations, and conduct multiple trials to average the results and reduce the random error. So, in conclusion, the experiment successfully demonstrated the principles of the specific heat capacity determination and the entropy generation in thermal system. The results were consistent with theoretical predictions, and the methodology, while simple, was effective. Implementing the suggested improvement could yield even more precise results and future solidify the thermodynamic understanding of the process.
So this is the list reference that we use. We have 6 reference that we use to make this report presentation. So that's all from us. Thank you.